Okay, let's do binary search question. Binary search is basically you start a point at the start and at the end, and if you can figure out the for any value, for any element, we can figure out where the target is relative to that element. So let's say, for example, we're searching for 9 in this case, and I look at 3. I'm looking at 3. Because it's sorted, I know it should be to the right of 3. Or if I find 12, then I just compare 9 and 12, so then I know it's going to be the left side of 12. If I know that information, then I can do binary search. And this applies to any kind of problem. So, in order to make it very quick, the search, we could just try some value in the middle, and then we would either know that the target is on the left side or the right side of the middle, in this case, and in either case we can throw one half of the array away, and we don't need to search that, and just we keep doing this, and so that makes it really fast. And so that would be a time complexity of O of log n. I wonder why it's log n. It's like the math behind it. Wait, isn't log n like log base 2 of n? That basically gives me the power. That gives me the power I have to take 2 to get n, right? So if log n is equal to 3, then this will be 8, right? Because that means I have to do 2 to the power of 3 to get 8. Right, so it gives me the power I need to get to this number. So if the time complexity is log n, where n is the number of elements, that's like asking how many times do I have to take 2 to the power of be able to get the size of this entire array. And that kind of makes sense. If I have half the array, then I just need to take this to the power of 2 again, another 2, so add 1 to the power, and then I'll jump from 4 to 8, and it kind of just works up like that. I feel that makes sense. Anyways, that's a little bit of a side thought. How do we implement it though? We keep track of the left and the right of it. And we maintain an invariant. So we maintain the invariant that L is definitely less than or equal to the answer. This is just one version of binary search. And we maintain the invariant that R is strictly greater than the answer. So we can say L is equal to 0. So the answer could be 0. So that's why I can set it to 0. And that's the lowest one I can do. And we can set R to be equal to something strictly greater than the answer. So that will be nums.size. So that's 1 beyond the end. And have a while loop. Since this is less than the answer, or less than or equal to the answer, and this is greater than answer, I know that they can never be equal to each other if I maintain these invariants. If they're never equal to each other, as soon as they're next to each other, then I know that low, L, would be the answer. In fact, I can call this low and high. So loop as long as they're not next to each other, which means while low is less than high minus 1. I want to check if the middle value, so let's get the middle value, low plus high divided by 2. If something about this middle value, some condition on this middle value, I want to set high is equal to mid, otherwise low is equal to mid. But what is this condition? So I know I can set high is equal to mid if this number is definitely greater than my target, because that's the same as saying that the index high is greater than the answer index. So if this is greater than the target, I can know I can set high is equal to mid. Otherwise, it's less than or equal to the target, so low can be mid, and that satisfies that. By the end of the while loop, they'll be next to each other, and I know that low would be the answer if it exists in the array. So in the case where it doesn't exist, return -1. Here I'm assuming that it exists, and I know that low would always be satisfied. It would be somewhere in the array, because low won't be ever be going left. It's always greater than or equal to 0, and it can't be, has to be less than high as well, because of the way I'm calculating the mid. So to check if it actually exists, then I know that I can do nums low, because low would be somewhere in the array. And if that's not equal to the answer, then return -1. Otherwise, just return low. If nums. Yeah, it seems to work. So that's we're searching for 4. Can't find 4, so let's search for 3. Nine. Okay, that seems to work. Let's run that, and hopefully it works. Okay, that works. The other approach, so some questions may ask you to find the last index. So in the case where there are duplicate elements, say 1, 2, 3, 5, 5, 5, 5, 6, 7, 8. Let's say I could return any of these indexes that correspond to a 5. But let's say the question asks you to return the first 5 or the last 5. What would the current implementation return in this case, if I'm searching for 5 in this array? Well, let's just look at the invariants. So low is less than or equal to answer. So I could set the low to be this one. But I know they'll be next to each other. So that means high would be here, but then high would then be equal to the answer, which would not satisfy this. So this actually has to be all the way up here. So my current implementation would find the index of the last possible answer. And if I want to switch it around so that I could have, so I actually want to return the index of the first possible answer, I would have to change the invariant so that high is greater than or equal to the answer, and low is strictly less than the answer. Greater than or equal to the answer, and this is less than the answer. Right. Which so that means, that just means I have to do greater than or equal to target, then high is equal to mid, and low is equal to mid, and then at the end I need to return high. So if high is greater, less than or equal to target, return -1, otherwise return high. I need to make sure that high is somewhere within the array, otherwise this will give me an error. Right now it's not. It's nums.size, so to guarantee that it's within the array, I can do nums.size -1. Problem is, low could be the answer, but I'm saying it's less than answer, so this actually has to start at -1. Right, so that's how I would change it to return the first instance of the answer, of an answer. Okay, let's see if that one works. Awesome, that also works. Okay, great.